What's the roadmap relationship between Swift for TensorFlow and mainstream Swift? Will they eventually be the same thing, or?
Yeah, that's a great question. So right now, the Swift for TensorFlow project, you can think of it as like a dev branch. Actually, it is literally a dev branch on the Swift project. And so what we do is we build things like automatic differentiation, we bake them, we get experience, and then we propose them and merge them back in the mainline Swift language. And a bunch of stuff has already been done that way. So the Python integration drove new language features in Swift. We proposed them, we got them integrated into the mainline compiler, and now they're shipping, and iOS developers can use cool things because of Swift for TensorFlow. Yep. So let's dive in. Now, I thought I would start with some really basic things to just introduce the language, just so you understand, you have some context of how things work, and then we'll get into some more interesting stuff. So this is a Jupyter notebook, just like you'd expect. This is Jeremy's Windows machine, which I will struggle to use, because I have not used Windows for a long time. It will be fine. It has a Mac keyboard on it, so it's super weird. It scrolls the wrong direction, but it'll all be great. So a lot of what Swift does looks very familiar to Python. So here I have some integers, 6, I have some math, I have print. It all works exactly the same as you'd expect in Python. One of the major differences in Swift is that you have this let and this var thing. And so let in Swift means constant, var means variable. And so it's super easy, and as Jeremy, I think, loves to say, in a workbook, just declare everything var, and then you don't have to worry about it, and then you can change it however much you want. But you can see if you declare a constant like pi, because pi should not change, right? It makes sense to use let. If you try to change a constant, you'll get this error message. And this error message says something like, cell 5, line 1. One of the cool things about Jupyter is if you hit Shift L, you get line numbers in here. And here you can see it's referring to cell 5, line 1. And it says, hey, if you go to cell 3, line 2, up here, you can change this let into a var, and now your code will work. And so it's trying to help you out here. So that's something that you'll see.
That's super awesome. And I'll just mention, like, for people watching that have a background in Swift programming, there's a tendency in that culture to kind of keep things closed, keep things constant, keep things private, and there's lots of good reasons for that. But when you're kind of getting into this deep learning mode, we generally represent flipping everything upside down, at least for the R&D and prototyping process, because you want things to be infinitely hackable, the way Chris describes. You want them to be var, so you can change them. You want to be public, so that you can see inside them. And so you'll actually find, like, there's been recent PRs to Swift for TensorFlow itself, where we're starting to change APIs in this way to kind of like make it so that people can look inside the covers and change things more.
Yep. So you may notice that we're not using a lot of types here, but Swift is a typed language. Types are actually a very important way that the compiler can help you, because you can detect errors early. What Swift does is it has a thing called type inference. And so when you say var x equals 4, it knows that 4 is an int, and so it'll default it to an int. Or if you say var x is equal to 1.0, it'll say that, oh, that's a float or a double. And so types in Swift are written with a colon here, and so you can say, okay, well, even though this would normally be an integer, actually make it a float. Swift supports important things like emoji. Emoji is totally better than Greek letters, Jeremy.
Yeah, so actually Chris asked me last week, he goes, Jeremy, yes, Chris, what? He's like, how do you feel like about emoji in notebooks and Swift code? And I literally said to him, Chris, they're fine as long as it's the pile of poo emoji and it's next to a cow. And Chris goes, okay, it's the pile of poo emoji, but it's next to a dog. Is that okay? So like, yeah, okay.
Yeah, we split the difference.
Yeah.
Yep. So, this is great power and great responsibility. If you name all of your variables pile of poo, then your code is, never mind.
Static confined.
Yes, descriptive, maybe. Yes. So let's talk about a few other things. So Python uses indentation. Swift uses curly braces. So I don't think that there's any, I'm not going to say one's better than the other. Curly braces are more commonly used, and so that's why Swift uses them. But they're basically the same thing. Just, you'll figure it out. How do functions work? Well, in Python you use def, in Swift you use func. Func, because it's a function. And so what this is defining a function, and you declare the inputs, the signature, x and y, and it returns a float, and you implement it with the thing you'd expect. When you call it, you pass pass keyword arguments. Swift is very opinionated about keyword arguments, and so if you say that this thing has X and Y as arguments, you have to pass X and Y. And so one of the funny things you'll see is you'll see this underbar thing going on right here. And this is saying that ignore, underbars ignore, just like Python, ignore the keyword argument, and so when you call it, you don't pass that. That's all that means.
Yeah, I mean, I've got to say, I love almost everything about Swift, except for 3 things. This is one of the 3 things. So like this bit I find awkward because like these positional parameters, you can't even change the order of them. Even though they're positional, you can't use them in a different order. If you do have that underscore to say you don't have to name it, then you're not allowed to name it. Yep. Like it's, I don't know. I find this bit nasty, but it's like everything, almost everything else I love about Swift, so I just put up with it.
This is also not my opinion of the right thing, but the argument for that is consistency of APIs is important, and it works fine. So tuples work pretty much the same way as they do in Python. You can use them to return multiple values, which is what we're doing here. So here we're returning 2 floats, and we're saying the first one is sine and the second one's cosine. You get destructuring, you get access to the tuples, all the nice things that you'd expect. One of the things that's different about Swift and Python, Swift has this thing called struct. And the way to think about it to begin with is it's just like a class in Python. Structs are super powerful though. They are more efficient. There's a lot of good things about them. They don't require memory allocation. And we'll talk about why that matters.
If you've got a C programming background, it's not much like that at all. So I would say, like, think of it more like a Python class than a C struct.
Yeah, exactly. And we'll show you a little bit about that. So here I have a complex F struct, and I've got a real and imaginary. I stick it in there. I can create one of these complex Fs by specifying these things. I print it out, and I get it back. And in Python, there's this thing called data class.
Yeah, so we've used data class, and it's interesting when I threw in a data class here, it looks almost exactly the same. There's some extra boilerplate we need in the Python version. For example, we have to put the 2 things on different lines. We can't put them on the same line. But overall, like a lot of things between Swift and Python, ends up looking extremely comfortable.
Yep. Okay. So now one of the bad things about this thing is you notice it's defined with floats. But complex numbers work with integers as well, and they work with doubles and lots of other things. So the way that Swift handles this is this thing called generics. And we'll talk more about the details of generics later, but basically what we can do is we can say, let's define a complex type, and complex works with any type T, and anything that is signed and that's a number. And that's what the signed numeric thing says. And so now what I can do is I can define the struct, and I can use it down here with integers and with floating point, and it just figures out that T is int or T is float, depending on what you use it with.
And this is something that Python can't do, right? So with Python, if we remove the data class, we could certainly then remove the float, and then we could have it untyped. But we can't say in Python, these 2 have to be of the same type, but I don't know what type it is yet. Yeah. So this ability to use generics lets us do some pretty powerful stuff right out of the box. Yeah,
and we'll talk about some of the really cool things that you can do that make it super flexible and super, there's some really, really powerful things you can do. So we've got our complex here. One of the things you can see we're doing is that just like in Python, you have computed properties and stored properties. And here we have a computed property. We can define a getter just in line. And so it's just a stored property, but you provide a body. It's quite simple. Here's a computed property doing a weird thing, but here I just have a computed getter and a setter, and it's pretty straightforward. This is very similar to C#. When you've got one of these, you can create some of these things. You can use the computed property, and it works just like a normal property. It's all very simple. Now, one of the cool things about Swift is that after you define a type, you can add methods to it. And this is something that might make you feel weird, but you can add methods on anybody's type. You can add it on your own, like we're doing here, or you can add it on standard library types, or you can add it on anybody's.
I mean, it doesn't make us feel weird. I mean, it doesn't make me feel weird, Chris, because like we do it in FastAI all the time. Okay. It's called monkey patching. But it's kind of something that we're told to avoid because monkey patching has weird, dangerous, undefined, strange behavior and things combined in weird
conflicts
ways. So is this monkey patching? Should we be avoiding this in Swift?
So this works in a very highly principled way that actually composes, and if you get a conflict, the compiler will ask you which one you want. This is not something you should feel bad about. Now here I'm defining an add method, and so I'm using this to add 2 complex numbers. I feel bad about this because there's a way to spell add, and yes, it's ADD, I guess, but I would rather spell it with plus. And so you can call a method on this, just like any other method, but if you want to add an operator, what you do is you just define func plus. And so instead of underbar add and all that jazz, you can just define the operators you want and spell them the way you expect, and they're just functions like anything else.
And this like already is getting at something that would be really nice to be able to do in Python, would be able to say like, oh, there's a whole bunch of different functions or operators with the same name, and they behave differently depending on what type I pass to them. Now, Python does have a standard library decorator you can use called single dispatch. We almost never use it because like every time we've tried to use it, it reacts in weird ways with everything else. But it's super nice that in Swift, as in many typed languages like this, it's very much designed for us to be able to say like, oh, here's lots of different types, and they all have different meanings of what, for example, plus means, and it just works.
And so here we're implementing plus on complex in terms of plus of its elements. And so we're just adding together the real and imaginary, and these are different pluses. One of the like mind-blowing things that's very different than Python is that you can define your own operators. And so some of us do lots of math, us not including me, but some of you all do a lot of math, and or you're working in a domain where you're doing quaternions or other cool things like that, and it's really nice to be able to use operators that are familiar to your domain. And so if you want to define a square root operator, then you can define a square root operator. And these just work, and now you can use a square root operator just like anything else. And this is one of the examples of Swift being hackable. Like there's a standard library that has a bunch of stuff built in and provided with in the box, but the stuff the standard library does, you can do too. And so we try very hard to not make the standard library be privileged. So that's like the super quick introduction to some random stuff in Swift. There's this guided tour here, which is really cool. It goes into other random stuff. And so if you want just a high-level introduction like this, you can go there. But let's dive into some more relevant
First, we
pieces.
have two questions.
Yeah.
The first is, does Swift support any debugger within Jupyter, similar to IPDB for Python, to set breakpoints?
So we don't have that yet. We have all the mechanics under the covers. So Jupyter's actually talking to a debugger. We just haven't wired it up yet. But that's one of the things we're interested in.
Okay, so that's probably coming.
I can't promise that,
Okay.
but the guy in the front row that built it all is smiling, so maybe.
And does Swift have something similar to Python's args and KW args?
Yes, in fact, we'll talk about that when we get to the Python section.
Oh, great, thank you.
Yeah. So it works a little bit differently. So let's talk about Python now, because we love Python, right? Well, Swift loves Python too. And as Jeremy helpfully pointed out, Swift's data science ecosystem is kind of pathetic. So Python is really important. And beyond the data science ecosystem and Swift being pathetic, you all know Python. And so you all know important APIs that are pervasively available. And there's no reason for you to relearn new APIs. Like if you know the APIs in Python, just use them. So let's talk about how that works, because I think it might blow your mind a little bit. So to use Python in Swift, you first import Python. Okay, this is just a library in Swift called Python. And then you use Python to import whatever Python libraries you want. And there's no wrappers, there's no build steps, there's no wrapper generator thingies. You just literally import NumPy, or here we're importing matplotlib. Okay? And what does this give you? This gives you NP. This gives you PLT, just like you would do in Python. And now you use it just like in Python. And so here I'm calling NP array. And this is, except for the let, this is literally what you write in Python. Okay? So we can now use this to do some cool stuff. And so here, actually, we're going to use this load-mnist function, and we'll see it a little bit later. It's in the 00 notebook. This is firing up TensorFlow and loading the mnist data set and plopping it into a tensor for us. Once that comes back, now we can use matplotlib. And matplotlib, we can use this magic incantation, this kind of like the matplotlib inline. We can then take the tensor that TensorFlow gave us, do all the NumPy stuff with a NumPy ND array, reshape it, and plot it out. And this all just works the way you would normally use matplotlib. And the cool thing about this is that Swift knows nothing about matplotlib. Like, it knows nothing about NumPy. It knows nothing about any of the particular libraries you're using. We literally just imported some random thing with strings, and Swift doesn't know anything about what you imported here. Okay? Yeah, so and so you may be wondering how this works, right? Because we're just using Python right from Swift, and how does Swift know what Python is? Well, the way to think about this is that we think about Python as though it has no types. But really, Python has one type. And that type is Python object. And Python has an internal representation of objects, and you can use dot on them, and you can call them. And so the way it works in Swift is that you have one type called Python object. So here when we use the type of, that's just like type in Python. It says, give me the type of NP, or give me the type of NP.array, or give me a type of the array that we got, or whatever. What it actually shows you is the type is Python object. And so Python values are Python object types in Swift. And when you dot them, when you call them, it's just using the interpreter. And so it just works in Swift because you are literally using Python as dynamically as Python is designed to be used. And you can actually go and look. And one of the totally brain-twisting things that you can do is you can import Python into Swift, import FastAI's Python libraries into Swift, and now go to town and just use all the standard FastAI cool stuff right from Swift, and it all just works.
So thank you to Omar SF for trying this. It's a crazy thing to try. And it's interesting how when you look at the resulting code, it's the same code that we, like at this point, you can't tell other than some slightly different syntax here and there, but it's all the same.
It's like Python with let and var.
One thing I'll say about this is this is a super cool feature that you should totally use to fill in the gaps that need to be filled in while this ecosystem doesn't exist. But then as soon as possible, fill in the gap, right? Because I don't want us, as a Swift for TensorFlow community to use this as such a crutch that we never write our own even better data frames library because we're always using pandas, and we always use matplotlib, so we never create an even better plotting library. We should use the crutch to allow us to get all our work done end to end, and then gradually replace it with bits that are more Swifty.
I mean, one of the awesome things about Swift is that it supports really well considered and beautiful APIs, and it was really designed for building APIs. But particularly when you're new to Swift, don't worry about that stuff. That's a problem for a different day. If you want to open a file the way you know how. Just use the Python file IO library. That's fine. You don't waste your brain cycles on that kind of stuff. So let's now talk about the idea of Jeremy's course here, which is building a machine learning library from scratch. And I think it's very quaint that Jeremy tried so hard to go down to the foundation and teach you how to build a matmul with a few loops and looping over an array and adding and multiplying floating point numbers. And I think that it's very, very nice how that he thinks that this is going down to the foundation.
No, Chris, it's matmul from scratch. See?
Yes. Well, so if that's matmul from scratch, then I think we should go down to the bedrock and actually talk about where float and arrays come from. But before we do that, I want to dive in and geek out just a little bit about compilers, because I think you need to understand, or it's useful to understand what LLVM and Swift and things like this are.
So Chris, what you're saying is that I cheated. I used array without implementing an array.
Exactly.
And I used float without implementing float. So
let's fix that.
Okay, I'm sorry.
So what is a compiler? Actually, we can do bonk.
Oh, look at you.
Touch screens. Wow, crazy. Okay, so what is a compiler anyways? And what is a language? So the way I think about this is that there's actually two unmovable obstacles in the universe. There's humans, which we're all kind of a pain to work with, right? Highly opinionated sometimes. And then there's computers, and they're really a pain because they are super opinionated. And so what languages are is they're a point in between. And different languages are different points in between. And some are optimized for working with humans better, some are optimized for working with computers better, but good languages work well with both. And so how do compilers work? Well, the way that it used to work in the bad old days is that if somebody wanted to build a compiler for x86, they would build a parser, the front end part of a compiler. They'd then build an optimizer to make the code go fast, and they'd build a code generator for the Intel PC or whatever it is that they want to target. Somebody else would come along and say, hey, I want a different compiler. I want a C++ compiler, and they would build a parser, they would build an optimizer, and they'd build a backend for PowerPC. Somebody else would say, hey, APL is really cool. Let's build a parser for APL, an optimizer for APL, and then a backend for ARM. And if you've noticed the trend here, there's a lot of reimplementation of all the things going on. And so what compilers have done is they've created funnel points. LLVM is one of these funnel points where you can make it so that lots of different language people can implement lots of different front ends, and lots of different hardware people can implement what's called the back end or the code generator, and now they can share a tremendous amount of code. And now you can get all the permutations that you want out of this.
And we should all thank Chris Lattner's master's thesis supervisor for forcing him to write his damn thesis and getting him to actually write LLVM version 1 in 1.5 weeks of Diet Coke fueled coding activity. This is the way we get things done, is give people a ridiculous deadline, and it happens.
Absolutely.
So, yeah.
And so the details of what LLVM is not really important, but this LLVM is what powers Julia and Rust and Swift and Clang that does C and C++. It's like a very common set of infrastructure that lots of things use these days. And if you're not very familiar with compilers and what optimizations are, there's a bunch of standard stuff that LLVM does, including constant folding, removing dead code, other things like the example I show here of taking an expression and pulling it out of a loop. This is something that in PyTorch, for example, if you do a multiply inside of a loop of 2 tensors, it's going to run that multiply every single time you go through the loop. But reasonable, more modern languages actually pull these things out for you.
So this is a fascinating example, right? Because normally if we're writing Python and you see, oh, I'm doing this work inside the loop redundantly, I can pull it out. That's something that I, as a programmer, have to figure out, right? And the fact that LLVM can do this for you, and other optimization systems in GCC or whatever, it suddenly makes you realize that compilers are something different to at least what I thought they were. I thought compilers were things that got in your way and complained until you did things the way they expected you to do them and took forever to run code that I would have finished yesterday if it was Python. But actually, working with Swift, and particularly with Swift for TensorFlow, has made me realize that these optimizations actually allow us to write code in different ways and actually be much more lazy about how we write code.
And this is as you think about a point in the space between the human and the computer.
Yeah, so we're actually going to show you something really mind-blowing next week where this is actually going to be used to basically make autodiff work. And it's like, it blew my mind when I found out about it.
Yep. And so now if you think about languages and different points in the space, there's a couple of different ways to look at this. One of the ways I think about it, ignoring the syntax pieces, which the syntax is always the first thing people talk about, is what are the atoms of the universe and how do they get composed and how do you build things out of them? And so if you look at Python, for example, if you boil everything down in Python, boil a dictionary down, it's a bunch of C functions. And then what the interpreter does, the Python interpreter does, is it decides what C functions to call in what order and on what data. And so the Python interpreter is slow, and so the Python program ends up being slow, even if the C pieces are fast. C++ is another language. C++ is a little bit different. C++, the atoms are built-in things like integers and floats and arrays and pointers and things like that. And then a C++ programmer can use structs and classes to build complex numbers or strings or its variable size array thing in the library. Right? It can do this because C++ is a fast language. It's also not a super well-considered language, but it's weird to me in C++ that array is hard-coded into the compiler, but string is a library feature. And why is that? That doesn't really make sense to me because strings and arrays are so similar. What Swift is it says, let's rethink all this. And so the primitives, the low-level atoms of the universe, are now things that LLVM, the compiler, knows about. And then all the abstractions you build, including floats, arrays, dictionaries, of course, the high-level stuff too, like layers, those are all defined in the library. And so a float is not a magic built-in thing. Swift doesn't like magic built-in things. Swift likes things that are hackable. And if something is interesting for a library developer to do, maybe you want to do it in your workbook, right? And so having an open ecosystem is very powerful. And so if you actually go look at the library that implements float, float is just a struct, just like the complex thing we were talking about before. In the middle, the inside of it is this built-in weird thing. That's an LLVM thing. And plus, on floats, isn't a magic thing that the compiler knows about. Plus is just an operator, just like we were talking about before when we defined square root. Just this one happens to be named plus or plus equals. And it's implemented with the LLVM magic.
So we're allowed to use float now, Chris?
Well, yeah, let's go look at the implementation. And so if you actually go look at this is the standard library that comes with Swift. Here you can see it implements infinity. It implements not a numbers. It implements add, pi, like all of the things that are in float is just a gigantic pile of Swift code. And the cool thing about this is that this means that you can implement low-level stuff like this too, and write in a workbook.